This is all lots of fun. But the reason why we do this, it seems an overkill for finite matrices, is that we would like to be able to compute this topological entropy even when partition is infinite. And that'll happen in dynamical systems because all our finite partitions are rough approximation to the correct answer, because all of them are coarse graining neighborhoods. All of them are using finite history in dynamics. And it's only in limit of infinite history that you get individual trajectories which have zero neighborhoods. So as we'll be approaching this, we'll actually be looking at larger and larger matrices. And these trace formulas are extremely useful to us. So in this particular case, this will not be true in general. The determinant of the graph will turn out to be something fancier still. That's called topological zeta function. And topological zeta function will be our bridge from naive view world of coarse partitioning to something that's actually exact for any deterministic flow. So what will happen in general, in our expansion so far, determinant is just few terms, but in general, as the matrix grows, it'll get bigger and bigger, and as the transition matrix goes off to infinity, there'll be some function which starts with minus, and then has in all length terms and goes from 1 to infinity, and computable numbers here. We have shown you a few examples where you compute it for finite matrices, but it'll be true even for infinite ones. So the way we think about this is that we know that we can write determinant 1 minus zt transition matrix as e to minus sum over prime orbits, because we know we can write as traces, and each trace we can write in this way. R equals 1 over infinity weight or prime orbit divided by repeat number R. What I've done here, I've substituted our trace formula into the expansion for every ordered trace, and what has happened is that we have lost in this expansion this length of the cycle, so that only the prime cycle shows up. I'll let you do the algebra. Now when I look at this term, I realize I can sum over R. This is e to the minus p. Sum over the R is called logarithm of 1 minus tp. So I was just summing this series. And again, we're assuming that these weights are small enough, they contain this generating functional factor z, so for sufficiently small z, all these things are convergent. But e to the exponent of sum of something to the logarithms is same as the product p of exponent to logarithm, these are inverse functions, 1 minus tp. So now we get a totally magical formula. It says the determinant of a prime cycle, determinant of any finite shift system, any symbolic dynamics that counts the allowed admissible trajectories, is actually an infinite product over all prime cycles in this very beautiful, simple form. And if I have to remind you, you've seen something like that before. There is an Euler zeta function which has a form p over 1 minus all prime numbers, power s, zeta of s. So this is called Euler zeta function. And if you had any number theory at all, you realize that this is the same thing as sum over all natural numbers n to the minus s, and goes from 1 to infinity. So this zeta function plays a very deep role in number theory. It's related to counting all prime numbers, studying the sums of all numbers. So you use zeta function to find out how many prime numbers as you increase your n, as you go further and further down. So this is called very often one, by analogy, is number theory. It's called 1 over zeta of z, which is hidden in here, is the number of product of all prime of this value t phi. So by now you should be pretty mystified, because I started something totally pedestrian. Finite matrices filled with zeros and ones. And now I've gotten you to the point where you're staring at the numbers here, which are, in this particular application, Tp is either 0 to the n, np, if p is allowed, or 0 if inadmissible. And now that's a determinant, meaning if I can determine zeros of this object as a function of my parameter z, I'll compute, for example, my topological entropy and maybe other objects of interest. So now there's much more, and if you like number theory and if you like solving problems, there is a whole bunch of extremely cute problems to solve. What we have learned so far is that we can express an asymptotic property of a system, the rate of growth or number of trajectory, in terms of traces, or in terms of zeros of a determinant of our one-step transition matrix, our instantaneous transition matrix. When you go to continuous flows, you'll be actually computing infinite future by knowing what happens instantaneously. Because one step is then, evolution, generator of the evolution. It's like Hamiltonian for quantum states.